Hello everybody. So in this video we're gonna introduce capacitors. Okay, as usual for any component we need for analysis in a circuit, all we need to know is the relationship between the voltage across the component and the current going through the component. Okay, as long as we know this relationship, we can use this relationship to analyze circuits with this component in it. Okay, so from physics again we know the current going through a capacitor is the capacitance times the derivative of the voltage. Okay, so now I'm not going to go through the entire physics of this, but if you want to remember this, I think you can remember the charge stored in a capacitor is equal to capacitance times the voltage across it. Right now, if you differentiate on both sides, the left hand side would be I of t, because the left hand side is a change in charge, which is the current, and that will be equal to C times the derivative of the voltage. Okay, so anyway, so this is the relationship between the current and the voltage. And now if you know voltage, then you can just differentiate it, multiply by C, and get I of t. Okay, now let's do the other way around. Let's say if you know the current going through the capacitance, how do you find out the voltage, right? So this will be solving a very simple differential equation, and which is I'm going to go through here. So I take this equation here and integrate on both sides, and I get this integral here. Okay, integral equation. Now on the right hand side, you have integral of the derivative of voltage with respect to t. Okay, then I make the substitution as u is equal to v of t, and the differential du will be equal to the derivative of the voltage times dt. Okay, this is how we define differentials. Then I'm going to use that substitution and plug it into the equation over here, and then I get the right hand side of this equation. Because I did u is equal to v of t, then t0 becomes v of t0, and t1 becomes v of t1. Okay, so and now du is this whole thing, so this whole thing is du, so that's why I have it here. Okay, so that's the right hand side, and the left hand side is brought as is. Okay, so now if I integrate the right hand side, I just get integral of du is just 1, and then I substitute the limits and I get v of t1 minus v of t0 times c. Okay, and the right hand side is integral. Now remember that we are assuming that we know I of t, so that means we can compute this definite integral. Okay, so that means I'm just going to rearrange this few stuff, and then I get the voltage at any given time t1 is the voltage at time t0 plus this part, right? If you notice this part here, that's the total charge flowing into the capacitor, right? Or flowing through the capacitor. And I divide by the capacitance, I get the change in voltage, right? So the final voltage is initial voltage plus the change in voltage. Okay, all right. So now if you know I, this is how you compute V, okay? And usually the initial conditions are that you start with the capacitor completely discharged. So at t equal to 0, you assume that the voltage across the capacitance is 0, in which case this equation comes down to a simple equation like this. Okay, all right, so that's how you can, if you know I, you can compute voltage across the capacitance. Now let's talk about power and energy. Right, again, if you have a component, the voltage drop is v of t from left to right, and the current I of t is the current flowing in the direction of the voltage drop. Okay, so then if that is the case, then the power is just given as v of t times t of t. Note that when you write power dissipated, or the power dissipated or power delivered to the component, you have to make sure that these are measured in the correct direction, right? So the I of t should be in the direction of the voltage drop v of t. All right, if that's the case, then power is given like this, and then I'm just going to substitute I of t is equal to c times the derivative of the voltage. Okay, and then I integrate on both sides. When I integrate on both sides, I get this integral equation, and then I make a substitution u equal to v of t, and then du would be the derivative of v of t times dt. Okay, and I make the substitutions over there, and I get this integral on the right. Okay, so now this integral is u du. That means it will be integral will be half u squared. I substitute the limits. And I get something. I get this right hand side here, and on the left hand side, note that the power is the derivative of energy, right, with respect to time. So using fundamental theorem of calculus, that definite integral will be equal to this. Okay, so now I know how to calculate energy too. Now, usually, again, you start with the capacitor completely being discharged at t equal to 0. That means the energy at time t equal to 0 is 0. And then that equation comes down to the simple equation here. Again, note that the energy at any given time only depends on the voltage across the capacitor at that time. Or the energy stored in a capacitor only depends on the voltage across the capacitor at that time. And it does not matter how the voltage got to that point. Okay. It only depends on the instantaneous voltage at that time, and that gives you the total energy stored in the capacitor, right? So that's about introduction to capacitors.